Okay, this is section 6.1. It's all about vectors on the coordinate plane. And we've done a little bit of adding and subtracting. We're going to take it to another level. If you look at your book, they're going to show vectors. Do they have they do have vectors with the angle brackets. So we've got two. We're going to show the vectors, and I'm going to show that they're equivalent. I'm going to show RS is going to be equal to PQ. And I'm going to give these points. This is example 1. It's -4, 2. So I'm going to go plot that. And S is equal to -1, 6. So the vector here is this. I can think of it in component form, which is going to be the easiest to compare, as RS, this arrow above it does mean vector, is 3 to the right and up 4. Let's take a look at P is 2, -1. And Q is 5, 3. I didn't draw this all that great. But again, I'm over 3, up 4. So vector PQ is the same thing, 3, 4. The key here to vectors, they have magnitude and direction, or they have X and Y components. They do not have location. So vectors go from a starting point. Sometimes we'll make that starting point the origin on the coordinate system. Sometimes we won't, okay? So a vector can go anywhere from any place. So we can talk about finding the magnitude of a vector. This is going to be example 2. And so here we've got a new P and a Q. So I can see that my vector, I'll put this on the coordinate plane, make it clear, starts here at P, goes down here to Q, and I went down to and over -2. So my vector itself is -2, -2. To find the magnitude, the symbol for magnitude looks like an absolute value. You can use functionally the distance formula, or I just put that there so I can do -2 squared plus -2 squared. That's 4 plus 4 is, oh, I need a square root. I'm doing essentially the Pythagorean theorem. But magnitude of PQ, not magnitude of PQ squared. You got to watch out for that. So the square root of 8, which I can reduce this factors of 4 and 2, 2 and 2, and my pair of 2's can get pulled out. I could use it straight up with the distance formula, which is the first x minus the second x, plus the first y minus the second y. Again, that doesn't really matter because I'm squaring the order. And that's square root of 2 plus 2 squared, which is still square root of 8. Example 3 is the vector operations that we've already been doing. So I'm not going to go through that. A unit vector. So a unit vector is a vector. Let's say I have a vector this direction, it's got 5. The unit vector is going to be the direction vector in the same direction with magnitude 1. Okay. And unit vectors will come up more as you get further along using vectors. The more you use vectors, the more unit vectors become important. So to find a unit vector, you simply take the vector, often in component form, and you divide it by the magnitude of the vector. So I'm going to call this vector v. Again, the book for vectors often just uses a bold to type vector. So boldface in this section is going to mean vector. So here's my vector. To get magnitude of v, so that looks like going the magnitude is the hypotenuse, which means I'm just using the Pythagorean theorem. That doesn't reduce. So my unit vector, I take the two components and I divide them by the magnitude. And that's a unit vector. That was example 4. For example 5, we're going to find the components of a vector. So I have a vector with magnitude 6 and an angle of 115 degrees. Remember, just like we have in trig, our angles will be measured from the positive x-axis. Positive going counterclockwise, just like this. Magnitude 6 means my hypotenuse is 6. And they've got a nice little clean formula. I find it easiest to just draw the picture. Finding the components means finding the x and y on my triangle. So I know that cosine of 115, and yeah, I'm looking at it from this perspective of this angle, but I'm going to use my 115 because that'll take care of my sign, positive or negative signs for me. And that is adjacent over hypotenuse, x over 6. So 6 cosine 115 is my x. I'll do parentheses there. Make it nice and clear. And that value is 5.44. No, that value is negative 2.54. Looking at the wrong one. That makes more sense. The y, again, I'll just do with sine. Is y over 6. So 6 sine 115. Really, once you've done this a bunch, you're just going to jump to step 2. Okay, once you get comfortable, like, oh, it's hypotenuse, I'm just going to jump to there. And that's perfectly fine. If you wait until you are consistently getting it right every time, you can just jump ahead. So what is my vector in component form? This. The magnitude of that is 6. The angle is 115 degrees. That's example 5. We can do the reverse where we find the magnitude and direction given a couple vectors. So here's a vector. Three, 2. This one's pretty straightforward. We'll use alpha for my angle. So magnitude I'm gonna call this is vector u. Magnitude of u equals, again, Pythagorean theorem, square root of 3 squared plus 2 squared equals square root of 13. Direction. You could use the square root of 13. I prefer to use the whole number as the tangent. So the tangent of alpha is 2 over 3, meaning alpha, my angle, is going to be the inverse tangent of 2 over 3, which is 33.69. So magnitude, square root of 13, direction, 33.69 degrees. This example 6, that's A, this is B. This one's going to be a little bit more tricky. So, -2, -5. Down here. This is going to become important on my direction. Angle I'm actually looking for here is theta, but I'm not going to get theta here. I'm going to get alpha. When I do that. So, first I'll start with, this is vector v. I'll start with my magnitude. Again, these absolute value signs mean magnitude. And that's square root of 29. Again, I'm just going to go to the, I'm intentionally doing alpha here. Jump to the inverse tangent. -5 is opposite over -2. So inverse tangent of 5 over 2 or 2.5. And just grab my calculator. And I want to be in degree mode, which I wasn't there for a second. And I get alpha equals 68.19. Um, 19. There we go. Nope, 20. I need to round this correctly. So that's not theta. That's from the negative x-axis, which means I need to add 180 degrees to this. Oops. I don't want alpha, I want theta. Theta is 180 degrees plus 68.2 degrees, which is 248.2 degrees. So magnitude, direction. They will usually probably write this off the positive x-axis. Okay, writing velocity as a vector. So we have a DC-10 jet aircraft flying at a bearing of 65 degrees at 500 miles per hour. Find the component form of the airplane. Recall that bearing is measured to due north. So I have this. I'm going to put my vector in red. 65 degrees there. I will finish out my coordinate system. So that's north. Bearing is measured going clockwise from due north. For simplicity's sake, I'm going to find this angle because that keeps it, if I do the angle to the x-axis, my x component is always going to be the cosine. Be careful on that, but Your x component should be cosine. Your y component should be sine if you use the angle to the x-axis. So x is going to equal 500 cosine of 25. Has to be the 25. And y is going to equal 500 sine 25. And that is 453.15, 211.31. The way this is written usually in physics is using what's called an I as a unit vector in the horizontal direction, j as a unit vector in the vertical direction. And they often write this in physics, or I hat actually. I hat. Your book just uses bold I's. So they're talking about the horizontal direction with an I hat and the vertical direction with a J hat. Useful information to know, not really going to be used much in this course, but good information to know if you're looking at doing anything with physics, or even if you're just going to take it for a general course in college. Okay. Example 8 says, pilot Megan McCarty's flight plan for her leaving San Francisco International Airport, flying a Boeing 27 due east. There's a 65 mile per hour wind with a bearing of 60 degrees. Find the compass heading McCarty should follow and determine the airplane's ground speed will be. So there's a 65 mile per hour wind. Assuming that its speed with no wind is 450. So what we're trying to come up with is 450 miles per hour due east, or this vector, 450, 0. We're going to have to add the wind, which I don't know why they're using AC, but we're going to call it the wind W. Okay. Vector W is currently 65 degrees and or 65 miles per hour and a bearing of 60 degrees. $65 miles per hour. Okay. So um never mind. That's not 150. That's not our goal. We're not talking about our goal. What she's actually going to have the plane pointed, she's going to set it to 450, and she's got to point it at an angle here because the wind is blowing it to the north. So I'm going to put the two vectors together. I'll show this in a second, how they add. She's going to have to point it theta degrees. That's not a very nice theta. And we'll probably put that angle in bearing later. So all the way to the positive x-axis. Theta. Okay, so first thing I'm going to do is get my components for this one over here. So that's 60 xy, not 60, 65. 65 is my magnitude. 65 cosine. Angle in here is 30. And 65 sine 30 is going to equal y. Again, if you're not fully comfortable with those yet, set up the sine and cosine as x over 65. That's going to give me components of w. And that is $56.29 and sine of 30 is half, so 32.5. What's happening here, we call this vector P for plane, is I need to add the two vectors together to get the actual motion. I did not notate that how I wanted. So what I'm actually doing is P plus W. What that looks like graphically, because vectors have no position, we add them tip to tail. And I'm trying to get what will result in being something due east, okay? My resultant goes, so we started with our 450. It doesn't really matter which one I started with. I can start with vector W over here and put vector P there. And they still end up in the same spot. So what I'm trying to ultimately find is going to be this angle. So I've got 56.29. And I know that I went up 32.5 here. Let's put it on the diagram here. That's 32.5. So this one, if it's going to be 0, has to be negative 32.5. Okay? So I know that about P. So P has a y coordinate that's known on the vector, a y component, to be negative 32.5. I don't know x. I could use the Pythagorean theorem. That's probably what I'll do to find x. Pictures here become really helpful. So c squared, I'm going to put on that side. X squared plus 32.5 squared. So I solve this for x, square both of them, subtract the 32.5 squared, and I get 448.82. So here's my vector P. I still don't have the angle, but that'll be just a second. To get the angle, I'm going to use an inverse sine. Yeah. Reason I'm using an inverse sine, let's do theta here. 32.5. Actually, let's move that over. And we're just going to use the positive because it'll give us the angle inside. You can use the negative, it'll get you a negative angle. So that's theta is going to equal the inverse sine. Again, I need to do opposite over hypotenuse. That's 32.5 over 450. And that's 4.14 degrees. Pretty sure they want this in terms of bearing. So bearing, remember, is measured due north. That's here. So I'm really just going to add 90. The bearing that they're flying at is 94.14 degrees. That's the flight bearing. The actual vector that they're traveling along is now P plus W. And the y's are 0, so I just add the x's. Y's go to 0. Add my x's, and I get 505.11. That's my magnitude. My vector is 0. Because it's perfectly horizontal, my x component is my magnitude. Okay, one last example. This shows up in physics a lot. Finding the effect of gravity. A force of 30 pounds just keeps a box from sliding down a ramp inclined at 20 degrees. Find the weight of the box. So here we've got a ramp, 20 degrees. I got a box. I have a force of 30 pounds. This could probably be friction. So I've got 30 pounds this way. I know I have gravity. This is my weight. So I'm going to call it W vector. There's this nice little thing. This is a right triangle. This up here is 70, making this inside 120. So I'm going to draw a right angle to essentially what I've done is taken my X and Y axis and I've tilted them. I'm going to draw a right angle to this axis. It's going to be a little bit off here. So this is Y. Y is actually a cosine here. If I look at that on my 20, cosine is Y. I know that if it's going to balance, the X has to be 30. Okay. I guess really all it asked me for was W. So W on the W side, I know that the sine of 20 is equal to 30 over W. So I multiply both sides by W to solve. And then I divide by sine 20. And that gives me a weight. Since this is a weight, this is perfectly straight down, 87.1 pounds. If I wanted it in vector form, it would be 87.71. And that is the end of section 6.1. So this is my weight.